in detail, and some other specification. Now I'll come to the applications. CRO can be used as a voltmeter for display of waveform, measurement of frequency, display of phase relationship, many things, many. This is only the tip of the iceberg. It is, as I told you at the starting, that it is like one instrument army. It can be used for many um, measurement purpose. Now I'll discuss waveform display, and through display we can measure many things, many information about the periodic time varying voltage waveform. Beyond that, it can be used for measurement in XY mode of operation. So when we choose XY mode of operation, then time-based generator is disconnected. Time-based generator is basically uh, as means as I told you earlier also, that when you will choose XY mode of operation, then time-based generator will get disconnected automatically, because all these are the part of the oscilloscope. It will get disconnected, and here one of the time varying waveform we apply here, and another time varying waveform, voltage waveform will apply here, and then outcome of these two will be certain pattern on the screen, that is called Lysage's patterns. And using these Lysage's patterns, we can make different measurements that I'll discuss now. So that's what it is written here. In XY mode of operation, time-based generator is disconnected from X plates. Two time-varying periodic voltage signals are applied to both the plates. Therefore, a time-varying signal is plotted against other, and resultant pattern is called Lysage's pattern. Lysage's patterns are used for making very important measurements. So this is what is the another way of operation of the oscilloscope, and both of them are very useful, and both the mode of operations are very useful for the purpose of measurement. Now I'm starting one application, frequency measurement. So CRO is operated in XY mode. So when we are talking about the frequency measurement, in that case CRO is used in XY mode. As far as frequency measurement is concerned, when your waveform is periodically time varying waveform, then one of the ways to use it in YT mode, you see, in YT mode, and then find out the time period of the waveform and take 1 upon time period, you'll get the frequency. This is one of the way. Another way is this, whatever I'm going to explain you here. So in this case, the signal whose frequency is to be measured is applied to the Y plate. So we are having, suppose, sinusoidal signal, and it is applied to the Y plates. I think I'm audible to all of you. Properly audible to all of you?
Yes, sir. Yes, sir.
Okay. So in this case, the signal whose frequency we want to measure is applied to Y plates, and another requirement is that an accurately calibrated standard variable frequency source is used to supply X plate. Means whatever time varying signal which you are applying to the X plates, to the horizontal plates in XY mode of operation of oscilloscope, that should be known, accurately known. That's why it is called accurately calibrated standard variable frequency source. The frequency of the standard source is adjusted till the Lysage's pattern is appears as a circle or an ellipse. Means obviously the signal which we are applying at the Y plate is unknown signal, and we want to measure this signal. And as far as the X plates, horizontal plate, we are applying the signal to the X plates through a known variable frequency source. Means accurately calibrated means known, whatever signal you are providing to, and it is variable also. So whatever signal you are providing to the X plates, it is always known. Now since it is a variable, so we vary the signal which we are applying to the X plates, and as you will vary, you will find that the different kind of patterns is appearing on the screen. We will keep on varying the frequency of the signal which is applied to the X plates till we get a circle on the screen or an ellipse, a circle or an ellipse. And when you are having a circle or an ellipse, this is the indicator that the frequency of the known signal source is equal to frequency of the unknown signal. So whatever is the frequency of the known, same will be the frequency of the unknown. So this is how, this is one of the way, when it is not possible. So this is one of the way to measure the frequency. Now it is not always possible to have a frequency source, variable frequency source, which can cover all the frequencies. Obviously, if we are talking about the certain variable frequency source, so it will have the certain range. So it is not possible to match the frequency always, not, to match the frequency of the unknown signal with the frequency of the known signal. When this is the situation, that what we do, so when it is not possible to adjust the standard signal frequency to exact frequency of the unknown signal, the standard is adjusted to multiple or sub-multiple of the frequency of the unknown sources, so that pattern appears stationary. So your pattern, whatever Lysager's pattern that is appearing on the screen, it will be appear stationary only when either both the frequency of the signal should be same, and if it is not possible, then it should be multiple of the frequency. Means your known signal frequency should be twice of the unknown frequency, or thrice of the unknown frequency, or 4 times of the unknown frequency, or other way around, it should be half of the known frequency, 1/4 of the known frequency, and so on, like that. So if you will make it like this, then when this is the situation, so you will find that we won't get the circle or ellipse on the screen. Circle or ellipse will find only when both the frequencies, signal frequencies, are equal. But if it is a multiple or sub-multiple, then we get the other kind of Lysager's pattern, and it will be like this. Means one of the example I'm giving you, it is like this. And using this Lysager's pattern, we can find out the frequency of the unknown. So here in this case, I'm giving you one example. Like if we are having one signal here to the Y plates, suppose this is unknown signal. Another signal to X plate, which is unknown, known signal, means frequency is known. So if you look upon these two, you'll find that the frequency of the unknown signal is twice of frequency of the known signal. Now, when we will apply this to the Y plate and this to the X plate, when your oscilloscope is working in XY mode, then obviously you see, because this is the Y mode, so you try to understand, you are already aware of the operation. Your electron beam will deflect in X mode twice, and in in X once, and in Y mode twice. So you see here it will go up and down twice, and one times in X during the same time the electron beam is moving horizontally to the screen. In that time, means it is moving here to here and then coming back. In that time, your vertical direction, it will move twice. So the plot will be something like that. It will plot one cycle like this, and then another cycle like this, because horizontally it is moving one time, going here and coming back, but vertically it is moving 2 times like this. So it will result into this Lysager's pattern. Now with this Lysager's pattern, how can we find out? Our objective remains same, that we want to know the frequency of the unknown signal, whereas this signal frequency is known. This signal frequency is not known. So that's what I had written. CRT spot travels 2 complete cycle in the vertical direction against 1 horizontal direction. Ratio of the 2. The formula is frequency of the signal applied to the Y plates to the frequency of the signal applied to the X plate is equal to number of horizontal tangencies divided by number of vertical tangencies. What we do, we draw tangencies. This is your horizontal tangency and this is your vertical side. Number of tangencies, horizontal tangencies will be 1 and 2 and vertical 1. So we'll take the ratio Fy by Fx is equal to 2 upon 1. So the Fy will give you twice of Fx. That's true. You can see from these two signals. So if you know the Fx, then you can find out the Fy. This is the way we can measure the frequency of the known signal using oscilloscope when it is operated in XY mode. Now this is very important method, you can say, or use of application of and it is important from the point of view lot of objective type of questions are made on this. So I want that if anybody is having any question regarding this method, you can ask it, please. Frequency measurement formula is very important, and this method is the researchers generally what they do in objective questions, they make different kind of Lysichus pattern and they give one of the frequency and then they ask. So method is that we draw the horizontal tangencies and the vertical tangencies and we count it and accordingly use this formula to find out the. So Fy upon Fx is equal to number of horizontal tangencies divided by number of vertical tangencies. Yes, please. बताइए, किसी को कोई क्वेश्चन है तो पूछ लीजिए. कोई क्वेश्चन नहीं है? Should I move forward?
Yes, sir.
You see different type of Lysichus patterns are here. Here, as I told you that when you are having a circle or you are having an ellipse, then 1:1, both the frequencies are same. Now here in this case, there are two horizontal tangencies and one vertical tangency. These two, this is now it is 3:2. Two type of Lysichus patterns are shown here, 4:1, and so on. Many times you will find. Let me open the point. Just a minute. So in this case, sometime you'll find this kind of Lysichus pattern, like this kind of Lysichus pattern. I'm sorry, this kind of Lysichus pattern. So in this case, if we are drawing the horizontal to count the horizontal tangencies, the method is like this. Either we drive vertical here or here. So this is counted 1, this is counted 1, 2, and this one is counted half, open 1, half. So it will be 2.5. And here in this case, it is 1, or we can count it half plus half. This half, so it also remains 1. This half and this half. So if whenever you are having a open ended Lysichus pattern, then the open ended will be counted half. Means we are drawing tangency, it will be half. Okay to all of you? Or even,
Yes, sir.
even in this form also we'll get, if you'll reverse it, then you will get this kind of. So in this case also we'll have this half. This one will be counted as half. So sorry. So this is different kind. You are having idea that now when we are applying two waveforms on X and Y, or two channels of the oscilloscope, when we are working as means they are having a phase displacement, we are having uh, one waveform like this and another waveform like this. So obviously these two are having some phase difference. So how can we find this phase difference? So with the oscilloscope, one of the ways this that we should display these two waveforms in YT mode of operation and then find out the phase difference by finding the time and then phase difference. But is easiest way is by using oscilloscope in XY mode. So the two waveforms of the same frequency and amplitude, but with different phase angle, are applied to vertical and horizontal plates of CRO. Now we are discussing the how can we find out the phase difference between two periodic waveforms. Obviously, the periodic waveform should be of the same kind. Means it is one sinusoidal, other should also. So I have taken one example here for general case. There are some special cases also, but first general case. Now, one of the waveform which we are applying to X plate is E sine 2 pi, means omega t. Another is E sine omega t plus phi. Obviously, the second one which is applied to the Y plates, it is basically phi angle ahead, means leading by to the waveform which we are applying on that. So then deflection in a, so when we are operating the phase angle, sorry, when we are operating the oscilloscope in XY mode, so because of these two waveforms, deflection of the electron beam will take place in X and Y directions. Suppose these deflections are dx and dy, because the k is basically the volt per division. So here we are getting a deflection of this and deflection of this. Obviously, your deflection will be proportional to the applied voltage, because this applied voltage applied voltage is basically uh, causing the deflection. So now because of it, certain because of these deflections, certain Lysiges pattern will be produced on the screen. Now for this Lysiges pattern, for t is equal to 0, dx, obviously you look at this when t is equal to 0. So the at t is equal to 0, there will not be any deflection in the x direction, in the horizontal direction, because as per the voltage, nature of the voltage that is applied to the X plate, it will be 0. And in Y direction, obviously when t is equal to 0, then it will be equal to ke sine phi. The deflection along the, when t is equal to 0, there is no deflection on the X plate. There is a deflection, only deflection in the Y plate, means Y direction. Okay. So thus dy at t is equal to 0 is deflection in y axis. When the deflection in x axis is 0, that is intercept on the y axis. So obviously when there is a no means when we are talking this about the Cartesian coordinate system, so when there is a no deflection in the x direction, only in the y direction, so it will be the intercept on the y axis. That's what I had I spoke about. Now, and if you look upon this ke whether Ke in this case or Ke in this case, it is the maximum deflection in x direction or in y direction, because the maximum value of the sine of an angle will be 1 in this case also, in this case also. So the maximum deflection in the x direction or in y direction will be Ke. Are you agree? All of you are agree? Whatever I am trying to explain here, are you agree with it?
Yes, sir.
ठीक है ना? जब t 0 है तो x डायरेक्शन में कोई डिफ्लेक्शन नहीं होगा इलेक्ट्रॉन बीम का, y डायरेक्शन में जो है इतना डिफ्लेक्शन होगा, और जो मैक्सिमम डिफ्लेक्शन हो सकता है x डायरेक्शन में और y डायरेक्शन में, दैट विल बी इक्वल टू Ke ओनली. Are you agree? So here if you look in these 2 points, when t is equal to 0, then this is the deflection that will take place on the y axis, and Ke is obviously the maximum deflection in the y direction as well as in x direction. That is not, but we are only concentrating on the. Now what kind of Lysichus pattern exactly will find when your two waveforms of the same frequency and same amplitude are having a phase difference of phi? We will basically get a ellipse like this, will ellipse. And if you look upon this, if upon dy is equal to Ke sin phi, if we divide it by Ke, then it will be sin phi only. इसको अगर हम divide कर दें Ke से, तो it will be sin phi. So sin phi will be equal to dy upon Ke. Or at t is equal to 0, you know, dy is basically the intercept of the y-axis, intercept of this pattern on the y-axis, because when t is equal to 0, then your deflection will be only y direction, and that will be equal to basically Ke sin phi. Just a minute. I'm so this deflection in y direction, deflection in y direction or on y axis when at t is equal to 0, at t is equal to 0 will be equal to this y int. इसको अगर हम नाम दे दें y int intercept. So it is y int. And this is basically equal to Ke sin phi. Are you agree? और हम इंटरेस्टेड हैं साइन फाई की वैल्यू मालूम करने, तो इसको हम लिख सकते हैं, इसको दिस होल थिंग वी कैन राइट साइन फाई is equal to y int divided by Ke. अच्छा, ये y int or Ke are the value of the deflection of the electron beam in specific at the specific time, where y int is the deflection of the electron beam when it is t is equal to 0, and Ke is the maximum deflection. तो अगर आपको जैसे मैंने बताया कि basically when you will apply this kind of waveforms voltage waveforms on XY plates. When your oscilloscope is working in a XY mode, then T will have all the values, so we'll have the pattern like this. So if we look upon the formula, so this what basically this is, we can write y int divided by y max, and y max, the maximum deflection, Ke will be maximum deflection in y direction, so y max. अब ये पैटर्न आ गया, अब इसमें y int कहाँ से ढूंढेंगे? So obviously this will be I try to make it basically it's not that much. I'll make another one. So this is your y int in this pattern, y int, and this is your maximum y. This is the maximum y, that y max. So by noting down the number of divisions here and number of division here, we'll put it, then the ratio will be equal to sine phi. But we are not interested in finding the sine phi, but we are interested in phi, so it will be sine inverse of this ratio. Y int sine inverse divided by y. So this is the way we can find out very accurately the phase angle between two waveforms. If anybody is having any question regarding it, you can ask, please. I'll take up one example, then it will be more clear to you. Having any question? This is again very means you will find many questions are asked in competitive examinations. You have been made given the y-intercept and the maximum the deflection in the y direction, and you are asked. So there are some more rules, obviously. So you can see that this is y int upon y peak, that same formula. Now there is one more rule, means as far as this ellipse is concerned, this ellipse will have its major axis along the first and third quadrant, or in second and fourth quadrant. Then the angle between two waveforms, voltage waveform, the phase difference will be between 0 and 90 degree, and between 90 and 180 degree when you are having second and fourth, and when you are having first and third, then it will 0 and 90 degree. So this is how obviously when you two waveforms are basically out of phase, then maximum it will be 180 degree, and minimum it will be 0 degree. So this is the way we can find, and this is the rule. Now I took one example. I'm reading, although example is big, but solution is very small. The voltage E1 is applied to the horizontal input, and voltage E2 is applied to the vertical input of a CRO. E1, E2 have same frequency. The trace is an ellipse. The slope of major axis is positive. Slope of the major axis is positive means this kind of, you are having this kind of major axis. हेलो हेलो जी जी बोलिए जी can see that this is the positive slope and this is obviously a negative slope. So the positive slope means your major axis is lying in first and third quadrant. So obviously whatever angle that you will calculate, it will be 0 and 90 degree. So now another thing is given the maximum vertical value is 2.5 divisions and point where means y max is given, and the ellipse crosses the vertical axis. This is your y intercept is given. The ellipse is symmetrical about the horizontal and vertical axis. Determine the phase angle E2 with the respect to E1. So just you put this formula and you'll get the ratio is take the sine inverse of it, then you'll get the. So this is the phase angle which is existing between these two waveforms. That's what you can. So this is how questions are asked and are solved. So if anybody is having any question regarding this topic also, then you can ask, please. Anyway, this is the general case, and this kind of pattern you will find only when you are having the angle between 0 and 80 degree, and some of the special cases are there like 0 degree, 180 degree, and 90 degree. In these cases, you won't find an ellipse. You will find um, different type of Lysage's pattern that I'll come to. But right now, means in excluding these angles like 0 degree, 180 degree, and 90 degree, on all other angles you will get this kind of pattern. Either this kind of pattern or this kind of pattern. Using this formula you can find out the phase difference. And what are the special cases when we are having a 0 degree means in phase, or phase opposition, or in phase quadrature. So that I'll discuss tomorrow in the morning in the first period. So I'm really sorry for today's fiasco that happened. My laptop was not working, and because of that, then I have to rush to the department, and that took a lot of time. I'm really sorry. Which class you are having now?
PLC class. After that.
It is going to be a CBCS paper, sir.
CBCS.
Someone has opted for PLC and other have opted for EDS.
Okay. So you will rush to different classes, no?